Welcome to the second part of my talk, where I will now show you the proof of this. So this talk is a contribution to the NCNGT, and if you haven't seen it, there's a first part which explains you what the theorem is about. So now we want to prove that. And in fact, I've already given you the idea before, which is we have our space, which is the stratum, and there are different cases, and we want to look at the different cases. So we will have 4 cases. And part of it is that we just have already small covering radius on that space, so there's nothing to do. So small covering radius, and by small here I mean that it's smaller than 18 times this. But that's not the only case. We have discussed in the first part that there are times when you have a large covering radius. So let's quickly think about how you can have that. Large covering radius means you have a disk in your space. Now your disk might either be embedded, and that's another part that I want to put here, and we call that the rich disk part. And I will specify later what we have in this rich disk part. Or it might be that this is not embedded, so it means the disk is wrapping around and overlapping itself. How can that be? For example, if you have a cylinder, then you might have this disk coming around like this, coming around like this, and it overlaps itself, and it can overlap much more. So the other case we have to look at is cylinders, and I want to distinguish between cylinders which have a lot of area and cylinders which don't. And a lot of area we call rich, so that's the rich disk, and not a lot we call poor, so we have poor cylinders, or we might have rich cylinders, and that some of the cases can overlap, but it's fine. We look at these 4 cases differently now. And I want to start with explaining you what we do in the poor cylinder case. For that, first the definition. It means we have a cylinder which has a height which is at least the covering radius of my space. And we are only interested in large covering radius because the small one we know what to do. So, and here in that case I want to call larger than 1 over square root of g, just because this is what we can do, and yeah, that's what we will assume here. And poor means that we have area of the cylinder being bounded from above by 1 over g. So we have a cylinder with bounded above height, bounded below height, bounded above area. That tells us that the circumference is also bounded from above, and on that circumference we have a saddle connection sitting. So we have a saddle connection of length bounded by 1 over square root of g. And this will help us now to figure out how large that space here is. Because it has been known for a while that when we have the measure of a part of the space where we have saddle connections, of a length which is bounded by delta, this has been proven by Mazur-Smiley, then this is c times delta squared at most. Some constant here. But we want to have here g going to infinity. And it's not clear how that constant c here depends on the genus. So we have to figure that out. And we did that based on a lot of other works. So I want to mention here Eskin-Okounkov and Eskin-Mazur-Smiley, but also the newer works of Agarwal and Jen, Möller, Sauvaget, and Sagier that we put in here. Oh, and I just see that I forgot, I put here, we want to know the proportion of this in the whole stratum, so I need, of course, the measure of the whole stratum here. Okay. And what we can do specifically here is, we are not only in the case of that there is a cell connection, but the cell connection bounds a cylinder. So that's much more specific, and for that case then we get that this is linear in the genus, and this constant here, the rest of the constant doesn't depend on the genus. And that's something that we put in there. Now, when we want to do our integral, we want to integrate this here, and we have the volume of the space here. But this here is bounded from below, not bounded from above, so integrating over that still doesn't, still will not give us directly the result. So what we do is we stratify this part here, the poor cylinder part, by looking always at cylinders of a certain height, between 1 over square root of g and 2 over square root of g and 4 over square root of g, and so on. So when we do that, we can write the part with poor cylinders as the union of these spaces where we have also an upper bound on the height. Okay, and now if we want to calculate the integral, then we have this integral that we're interested over, just over this space here now, the covering radius. I'm writing it sloppy now. And then what we can do is we can bound that by integrating just over these pieces of the space. So we have here always this n, which means we have also an upper bound on the covering radius. And when we calculate that now with the help of this piece here, then we get actually a number, which is, there's a constant, C1, and then we have 1 over square root of g, and then we have, coming from here, this measure. But that measure here is fine, because what we want actually is dividing by the measure. So that's exactly what we get here then. So we know that in this poor cylinder part, the average of the diameter is this here, which is, for large G, smaller than that. So we know what to do when we have a poor cylinder. And very similar to that, we do the case of the rich cylinder. There it's a bit more calculation. We need to adjust this formula here, saying it bounds a cylinder of a certain area, so that we can do the same things here. And then we stratify by area and by height and do the similar calculation. And get the same, just with a different constant. Okay, so these two cases we can solve with the help of knowing something about the measure of the so-called thin part here. So now we know about the poor cylinder case and the rich cylinder case. Let's go to the rich disk case. To remind you, rich disk means we have a large embedded disk. Now what we want here is, we want to find a way to take all the translation surfaces in this part and find a map that takes this part and scales it up a lot. So it means that has a large Jacobian, and this will tell us that in the beginning it must have been small, because otherwise I can't make it much larger. So this is what we want. We want a map, and that this works, we need it to be finite to 1. And this map that we can find here, what it will do is we will take this large embedded disk and take a square in it. And then we remove this square. Then we don't have a translation surface anymore, but we can glue these sides and these sides, and then we get again a translation surface. And so we have taken some area from the rich disk, and now we distribute all this area to the rest of the surface. So we have first made it smaller, and then we make it larger. And the trick here will be that making it smaller has a constant Jacobian, and making it larger has a large Jacobian. So this map we call the taxing map. And it's defined on that part here where we have rich disks. And then we take it and remove a square. But when we do that, then of course we don't land in the same translation surface stratum again. Because here we had singularities kappa. But now we introduce a new singularity. So we land in H kappa 2. And when we start with area 1 here, we now get something with smaller area. That's the whole point. Okay, and then we scale it up. And what we get is, again, something in that stratum. Now, let's talk about the Jacobian. So, I want to draw you some pictures. Taking something in the rich disk case means we have this whole stratum, we have the level sets of area. We take this piece here, that's perhaps the rich disk. So we have this cone. So let's not only look at area 1, but all areas smaller than 1 for a technical reason, I'll say it later. So we have this cone here. And now we remove this, so we land in a different stratum. I just can't draw that it has more, that is a different stratum, so it will also have 2 dimensions. And then we have a different piece, perhaps like this piece here, and the whole cone here. And now we are not on the level set of area 1, because we have removed area. So when we do this here, we scale this up. So we start with this piece here, but we scale it up to area 1. So where we really land is in that whole cone. Now what is the Jacobian of something that does that? This is exponential in the number of dimensions. So here we would get something in G, And because of what exactly the scaling factor is, you see this is why we put the log g in here. Then we have e to the log g, and we get something polynomial in g. And this Jacobian is approximately 1. Well, let's say it's a small number. Okay. So we have a finite to 1 map, because there are only finitely many pre-images for one translation surface here, which has a large Jacobian. But if we want this to help us, then these spaces here need to have the same dimension. So we will also look here at smaller equal to 1, and also here, because we have a neighborhood here coming from this. But then still, they don't have the same dimension. This is 6 real dimensions smaller than that. So what can we do? The map is defined as taking out this square. But nobody says we need a square here. We could take a parallelogram. So we can here remove a parallelogram, in fact. So we can wiggle the vertical edges a bit, the horizontal edges a bit, and also we don't have to position it in the center of the disk. We can also wiggle that a bit. This gives us 3 complex dimensions or 6 real dimensions. And now these two things have the same dimension. But when we take the image of this here, then it's scaling up polynomially in G. And we let our G go to infinity. So the pre-image here must have been smaller. But for that we also additionally need that this here lives in a stratum which is just a little bit smaller than that, like it's this stratum. And they have approximately the same measure. So let me write this ingredient here. So this lives in the stratum H1 kappa, and that's approximately the same measure as if I have another singularity if we have large genus. So there are many reasons why we look at large genus. Okay, and what we get then is the image in this is cannot be very large. I mean, cannot be larger than that. So the image here had to be small, the pre-image. So the measure of the rich disk part in relation to the stratum in which it lives is small. And we can calculate what this small means. And then we can look at the integral that we are interested in. So we integrate only in the rich disk case now. And important here is that this covering radius is bounded, because this disk here cannot be arbitrarily large. It's embedded, and area is 1. So the diameter of the disk is bounded. So we get something bounded here. So essentially what we get here is some constant times this here. And when we calculate it out, then it's smaller equal 1 over 45, square root of log g over g. And that's the log g over g that we want to have here in the square root. So what we get is that in these 3 cases, this is also done, we have that the average diameter is smaller than this. Here it's also smaller than 18 times this. What we can do is we can just add up all the 4 integrals. And that's why we have a 20 here. There's 18 plus something small, small, 1 over 45. So this is this number. And by that we have, this is clear from the beginning. And by that we have proven that the average diameter of a translation surface in a stratum where the genus of the stratum is going to infinity. for large values is smaller than these 20 times square root of log g over t. If you have any questions about this, then please come to the office hour at the NCNGT, write a comment there, send me an email. I'm very happy to answer this, and I'm very happy that you even watched the second part of my talk. Thank you very much.